properties, better bioavailability properties, better solubility properties, that type of thing. We use the same software, the same hardware, and the same general workflow to do all three of these. And so depending on the type of study that we're doing, we can actually do studies at different stages to affect different, impact different parts of the process. So why is it important to have an integrated and automated crystallization workflow? Well, polymorph studies in particular offer a number of challenges. Typically, one wants to do this very early on, and typically in early development or late discovery, then the amount of API is very limited. However, one wants to do extensive screening because you'd like to find the most druggable form so you can advance the most druggable form at an early stage and know which form you're taking forward. So one wants to do a very wide screening, but if you do this manually, and many of you on the phone probably know, this can be very labor intensive to do a real broad screening. It can be very time consuming. So there's a real desire to try to do this. So our solution has been to miniaturize the experiments to try to get more data using less material. We run many more experiments and do it in parallel. So and we'll talk about this, but we typically do about 400 experiments all in one shot to try to shorten the screening cycle times. And we integrate the automation and the analytical tools to get data much faster and to enable faster decisions. So I'm going to talk about the workflow. We do these in 96-well formats. However, the format that we do is a very unique type of plate. It's a sandwich-style plate, shown here in the picture. There's a picture of a bottom plate supporting a glass substrate, which is shown there. On top of the glass substrate is a top plate with a number of through holes that seals the bottom plate with a series of O-rings forming 96 individual wells. We then can transfer over a variety of different solutions. We can do different types of crystallization processes in these wells, generate different types of crystals, isolate out, remove the solvent, and what you're left with is solids that have been isolated on a glass substrate. That glass substrate can then be removed from this crystallizer, and it has a barcode, so when you take it to different stations, you can scan in the barcode, and you can do microscopy analysis. You can then take that same plate and go on to do Raman analysis. You can then take that same plate and go on to do X-ray analysis. So we're getting a variety of analysis, and all the analysis happens off the exact same set of samples. Okay, we're going to talk a little about specifically how the workflow works. We're going to talk a little about some results. As I said, we try to explore very broadly. We do this with a very small amount of material. It'd be very typical for us to start with something on the order of between 0.5 and maybe up to 2 grams of sample, depending on the known solubility of the compound, what stage of development it is, and how one wants to explore. And we will generate 384 individual unique crystallization experiments. And the way we do that is we typically do a design where we'll create an initial master plate or a slurry plate. Within that plate, it typically explores a variety of different chemical compositions. So if we're doing a polymorph study, what we would have is we'd have 96 different solvent compositions, which we generally generate by doing different solvent binaries to try to cover a wide range of potential solubilities of the material. We then take that material, so we'll dispense our drug. We'll dispense it either as a solution, or we'll dispense it as a solid. We dispense our co-solvents on top of that. The plate is sealed. We heat the plate up to a temperature of choice. Typically, it's either 60 degrees or perhaps as high as 90 degrees Celsius, depending on the solvent choice. We'll equilibrate for a period of time to allow things to come to equilibrium, and ideally generate a number of saturated solutions. We'll then want to filter that material so we can eliminate any possible seeds and generate a number of novel crystallization. So Symix has a particular type of filter assembly. I mentioned this earlier. The robot actually takes, and there's a picture of this down below, we use our heated tip to extract out and aspirate a hot solution out of the slurry plate, keep it at temperature, and pass it into our filter plate. The filter plate is also heated. We can filter this at temperature. It's a sealed filter plate, so if you're doing a variety of organic solutions that are hot, you don't see evaporation. Each one is filtered uniquely. The robot then cleans itself, it cleans the needles, uses the needles to reach down through, grab the filtrate, pass the filtrate on to a series of additional plates. Each of the additional plates we then use to generate an evaporation crystallization process, precipitation into antisolvent, and a controlled cooling. The controlled cooling, we typically do something like a cubic cooling over a period of time, generally between 8 to 16 hours of time. We also take some of the liquid supernatant and do an LC analysis, giving some indication of solubility and an indication of the stability and whether we're seeing any degradation of the compound as well. So from that, then, we actually have 4 plates. We have an evaporation plate that we've generated solids, a precipitation plate, a cooling plate, and we have an original master plate, which serves as a slurry type of experiment. Each of these is run in one of those master crystallization plates I talked about. So each of these, we're able to isolate solids on one of those flat glass substrates and generate a potential array of 96 potential crystal samples. So each of these plates we then take on to a series of analytics. The analytics are all integrated through a software. They are not integrated physically, but in this particular case, we get a large bit of impact. A researcher pulls the samples off, walks it over to the appropriate analytic, reads in a barcode, and starts it up. And then the instrument itself goes through and analyzes all 96 samples, saving the data to the proper place in the database. And we're showing here an example of a birefringence set of images generated from a polarized microscope with an automated station. And down below, we're showing a series of X-ray samples that have been sorted, looking at 2D X-ray diffraction patterns. From there, we then will go through from the analytics. We typically then generate a series of scale-up experiments once we've done the initial sorting. These scale-up experiments will go from doing, whereas the original library has something on the order of 1 to 2 milligrams per sample that's generated. A scale-up experiment would be to generate something between 25 and 50 milligrams per sample. This is enough for us to reproduce the initial birefringence, Raman, and X-ray types of results to verify that we're reproducing those, as well as enough to do full characterization in some of the destructive tests, things like NMR, DFC, PGA, Carl Fisher, perhaps DBS, and ion chromatography. We're able to do all 384 crystallizations, do full characterization and scale-ups, and generate data within 10 days to get answers, which is very, very impactful. So I have a few examples. This is examples from a salt selection results from a single screen. As I mentioned, we generate 4 different types of crystallization processes. So these are results from the four different processes. The upper left shows the master plate, or slurry plate. And you can see the white areas and the white wells show a high degree of solids, and things that are very white tend to be things that suggest a higher degree of crystallinity. The upper right shows samples that have been generated from an evaporation process where samples have been pipetted over and allowed to evaporate down to the solids. The lower left shows a set of plates generated from precipitation. So we're precipitating into antisolvents. Here you can see there are not as many wells as in the slurry plate, but there are some wells that are showing a high degree of solids, since it's a unique process to spare. And the lower right shows a controlled cooling process, where we've gone through a controlled, software-controlled cooling of the plate to generate crystals as well. Each of these plates can be taken on. Here we're showing the same plates, and we're showing data from X-ray analysis. So each of these plates